So it's my pleasure to be back here at this conference. I gave a talk here last year, 2 years ago, and I'm very excited to see the continued growth of the Indian C++ community. So my name, as Anka mentioned, is Bryce Adelstein Lelbach. My primary area of expertise is parallel programming languages and compilers, and I've served in leadership roles in a number of standards bodies, including the C++ community. I work at NVIDIA, and we make parallel processors, mighty fine ones. And there I'm a principal architect, and I drive our strategy for HPC programming models, C++ compilers, and C++ libraries. And I am here today to talk to you about AI-assisted software engineering. Let's see whether the clicker is going to work. There we go. So I am not an AI expert. I have neither the knowledge or the desire to explain how large language models like GPT work. I want to focus today on the applied science of AI, not the science of AI itself. I want to focus on how we can use AI technologies to transform how we develop software. So the applications, how it will impact us day to day. However, that said, I'll give some explanation of what large language models are. So large language models, like the ones used in ChatGPT, are neural networks with billions or trillions of parameters that are trained on massive quantities of unlabeled text. We interact typically with large language models by sending them a textual context, which usually begins with a prompt. The model then generates a response, which will be added to the context. The interaction can be continued by adding more textual input to the context. The model will evaluate everything in the context, including its own response, and then generate a new response. However, the size of the context is finite. As we add more input, older input and responses may be dropped from the context. Large inputs could be rejected altogether. So context size is one of the major limiting factors of large language models today. And this limit especially impacts the application of AI to software engineering, as we'd like the neural network that we're working with to have access to all of our code and the latest version of all of our code. So neural networks themselves aren't the end game of AI. They are just the building blocks. Simple AI systems may be built on top of a simple interaction with a single neural network, but there is much greater potential in complex AI systems that are composed of webs of neural network agents and other actors, such as information retrieval mechanisms and execution environments. So now I want to shift focus a little bit and let's talk a little bit about what we do as software engineers. What does our work actually consist of? What sort of tasks do we do? So when I've given this talk before, sometimes I've asked for the audience to give me some answers, and people will say things like, we fix bugs, or we stare at a debugger for hours, or we write code, we design systems, we write documentation, we create applications, all things like that. Now, I think that all of those answers sort of break down or are correct, but they ultimately fall into two different categories. There's two different kinds of tasks that we do. The first is creative. We create code, interfaces, libraries, applications, systems, documentation. We create all of those things. We also hopefully design these things before we create them. Of course, that's not always true. And we plan and we architect. And we analyze. We analyze code, results from code, diagnostics from code and compilers and tools. We debug. We review code. We review design documents. And I believe that this second task, this second kind of task, these analysis tasks, is where large language models shine. They are great at taking a bunch of data and extracting information from it. Let's take a look at an example. Imagine that our CI fails on our PR with this diagnostic. What do we have to do to understand and fix this problem? If someone submitted a bug report with solely this diagnostic, what would we tell them? Well, we would probably tell them like, hey, this is not enough information. Like you need to give us some additional context, right? We need to be able to see your source code. Working with open source, one of the most common types of bug reports that I'll get from somebody is they just give me a diagnostic without sending me any of the context of their source code. And I'm like, I can't tell you what the problem is without seeing your code. So we need more information to be able to interpret this diagnostic. So how do we identify what information we need? Well, that breaks down into a couple different tasks. First, we need to do some classification. What sort of tools are involved in this diagnostic? What programming languages, data formats, etc., are being used here? And then also we need to identify what sources and what other information we need. What files or resources do we need to access? What source locations, code entities, or content do we need to extract? So we want to have the large language model analyze the information that we have, the diagnostic, and determine what else we need for it to be able to diagnose the problem. Then we'll use the appropriate tool to collect the information that the large language model has determined that it needs. And we can iterate on this process until the large language model has all of the information that it needs. So we had the following source locations in the previous diagnostic. To build a context for the large language model, we could just load those files and take a few lines before and after each location. We can't load the entire file because remember, context size is limited. So we can just load each source location and take maybe plus or minus 5 lines around that location. So because large language models are limited, we really do want to stay within a certain context size. And we also don't want to provide too much extraneous information to the model. Even if we had a much larger context size, we don't want to provide it with more information than is relevant, because that might confuse the model and send it off down the wrong course. We really want to tell it only what it needs, only what is actually relevant to solving the problem at hand. So here's the source code that we actually wrote. This is the first location here. Does anybody see the problem yet? This bit of context is actually pretty useful. It shows us the root of the issue, this source code that we actually wrote. So here's the next source location. It's the plus or minus 5 lines from the algorithm header. Now, this is a little bit less useful context information. This tells us other headers that may be relevant, but not really much else. So one thing we could do here is we could iterate, we could look through this and we could determine, oh, hey, there's 3 more headers here. Let's load those in. So here's the next piece of code, and this is somewhat useful. The error that we've gotten has something to do with transform, and this is probably the relevant overload. However, there's a few things missing here from our source window because we just arbitrarily said we're going to take plus and minus 5 lines. So we haven't gotten exactly everything that we might have wanted from this particular source location. So first, we've got the whole signature of the function, which is great, but we only have just the start of the body of the function. So that's not so useful. Also, it looks like there's a comment before the function signature. It would likely be useful to include that comment in the context because it's probably a comment about the function itself, and it's probably a comment in plain English, which is great input to the large language model that is designed primarily for understanding plain English. So extraction of source locations based on file location is fairly easy to implement, but it may not be the best approach to crafting a good context for the AI. Instead, we could identify what specific code entities we need to see and use language-specific tools to extract code for those entities. For example, the Clang API for C++. And if we were to do that, we might get a list of entities like this, like, hey, we need to see the function stood transform. We need to see this type stood vector int iterator, and we need to see this lambda in this source location. Some of you may be wondering if you can just train or fine-tune the model with your code base to avoid having to do this context creation. That's certainly an option, and there's a lot of research being done there. However, that's not always going to be as feasible, flexible, or useful as you think. Are you going to retrain the entire model on every commit to your code base? Are you going to retrain it for every commit on your local branch? If we're trying to build a tool that understands our compilation errors, it really needs to have up-to-date code. And even if it is trained on the latest, changes on your local branch, it's still valuable to provide only the relevant parts of the code in the context, even if you've trained the model on your code base, because that tells the large language model, hey, here's the relevant parts. It's still useful to go through this process of building up a context that has just the relevant information. So now let's design a workflow for a tool that identifies and fixes this sort of programming language diagnostic. So we start off with our input, a diagnostic. This could either be manual input from a programmer, or perhaps more usefully, the AI tool could be integrated into our CI and receive the diagnostics directly from automated builds and tests. The first thing the tool will do is ask an AI model to identify what tools and programming languages are involved in the diagnostic. We have it respond to us in JSON so that we can use it programmatically. This classification is useful because it will allow us to select language-specific tools to do things like code extraction. Next, we ask the AI model what source locations or code entities we should show it to help it identify and fix the issue. Now, this might be a different AI model or an AI model that has been given a different prompt than the one that we used in the previous step. It may be something that's a model specifically designed for source location or extraction. Again, this model will respond to us in JSON. And now that we know what languages or tools we are working with and what source locations or code entities we need, we can use the appropriate frameworks like the Clang API to extract the code that we want. Then we send that extracted code to the AI and ask it to explain the issue for us and propose a fix. We get the explanation back as natural language text. But for the fix, we ask for a patch that we can apply to the code base. Then we can apply that patch and rebuild and rerun our tests. If those tests pass, that's great. Then we can automatically send a PR with the patch and the explanation. If the tests fail, well, then we've got some sort of diagnostic. And we now have an AI tool that helps us fix those. So Of course, you'll probably want to limit any iteration that you do here because those GPU cycles are pretty expensive. So what was wrong with that code in our example earlier? I'll let the tool explain. So this was our code, and I didn't give you much time to see it or to think about it, and that was sort of intentional because I want to demonstrate that you don't need to. You can just have a tool explain it for you now. So the AI says the problem is that you're not providing an output iterator as an argument to std transform. The function has the following signature, and then it accurately shows the signature for transform that we should be using. And it says it requires an input iterator range, which you provided with v.begin and v.end, an output iterator, which you haven't provided, and a unary operation, your lambda function. To fix the issue, you need to provide an output iterator as well. If you want to use the same vector for input and output, you could use v.begin as your output iterator. Now, this example came out of an actual piece of code that I wrote and that I made this mistake and was confused about what I did wrong. And its explanation was actually exactly correct, and its proposed solution also was exactly what I wanted because I wanted to do this in place. But I spent maybe 30 minutes, maybe an hour trying to understand what was wrong here. Whereas it took the AI tool, a matter of seconds to compute the right answer. And I think that when we build a sort of analysis tool like this, we can build something that's going to be maybe 90–95% fidelity. We can build something that's going to be very good at solving this sort of analysis task. Large language models aren't always so good at creative work, but at analyzing data, they are often much better than humans. And here's the patch that it came up with, which again is correct. It just adds in the additional iterator to do this in place. So my colleague Emery Berger, Nicholas Van Klempen, and I built an early form of this tool, which we call CWhy. It's on GitHub. Go check it out. It's far from perfect, but I'd say it's better at, identifying problems than fixing them. But I've found it incredibly useful, even when it's wrong, because it usually gets me headed down the right path. Now, one of the major challenges I've seen when building this tool is getting large language models to reliably output in the correct machine readable format, like CVS, JSON, or patches. And that makes it really challenging to build a reliable tool. So for example, extracting sources from the diagnostic in our earlier example really seems to confound some models. So on the left, we have the correct source locations. And on the right here, we have some of the responses from GPT 3.5. We use GPT-4 in our tool, but I want to show one of the reasons why we use it instead of GPT 3.5. So in this one, it's mostly right, but it misses the algorithm header. And it also duplicated some of the answers. In another response, it thinks the only source location is test.cpp column 6 or line 6 9 times. Also, sometimes it decides to just not follow the CSV format that I requested. Here it gave me colons instead of commas. Sometimes it just drops the line number entirely. Sometimes it includes explanatory text before the CSV that I did not ask for. Now, GPT-4 does do a lot better with this task than GPT 3.5, but it still does make mistakes sometimes. It's not reliable to the degree that we've come to expect from software. Google's BARD model is notoriously bad at outputting in a specific format. There was a thread on Twitter recently from Riley Goodside, who's a prompt engineer, about how difficult it is to get BARD to give you clean JSON without any explanatory text. He tried some simple prompts, no luck. And then he tried a more detailed prompt to convince BARD that it did not need to give him any explanatory text, to no avail. Naturally, the next step was for him to tell Bard that if it generated anything non-JSON in its response, then an innocent human being would die. And that did seem to do the trick and to give him clean JSON. But it is going to be very challenging for us to build tools with large language models if we don't have a way to get machine readable output from them that we can feed into other tools in a reliable fashion. One of the great things about large language models is that we can interact with them in natural language, but the problem is that they often want to interact with us in natural language, whereas sometimes we want our end of the interaction to be in natural language, but we want the response from them to be something that is purely machine readable or code that can be compiled and executed. And so that disconnect is one of the challenges of this field. And likewise, reproducibility when working with large language models is a huge challenge. Typically, when we run code with the same input, we expect it to produce the same output, unless, the code is a random number generator. Now, unfortunately, AI models are essentially fancy random number generators. We're in the exciting experimentation phase of the recent large language model boom. Everyone is going and building cool tools like cwhy, but has anyone thought about how we're going to unit test these things? There's two major components to reproducibility when working with AI models: reproducibility across sessions of the same model version, and reproducibility across models and model versions. Some models and APIs like GPT 3.5 and GPT 4 have a temperature parameter, which is usually a value between 0 and 1. If it's higher, you get more random and more creative results. The ChatGPT web interface defaults to 1. If it's lower, you get less random results. If you set it to 0, repeating the same prompt will usually, but not always, give you the same output. So by controlling the temperature, you can get mostly reproducible results, although they may be lower quality. And it's worth explaining briefly why these models have any degree of randomness. And the way that these models are working is that essentially it's attempting to predict what the most likely or the most probabilistic response to your input. And it's doing that based on this huge neural network that's been trained on all of this text. And sometimes the answer of the absolute highest probability response that it has is just wrong. And by introducing this degree of randomness, these models are able to explore different paths to giving you an answer. Instead of just always going down one particular path, it can explore multiple different paths. Because when you give it an input, you sort of imagine the neural net is like this entire graph or tree of all the possible responses to all possible inputs. And as you give it a prompt, it begins exploring some branches of that tree that represent reasonable answers to whatever the prompt is that you gave it as an input. And essentially, the randomness allows you to see multiple different branches instead of just always getting back the same thing. However, for software engineering, for things like unit testing, for building reliable tools, this can be a little bit of a problem. Bringing these things to production, making robust and reliable things can be challenging. There's also the issue of the model itself changing underneath you. If you're using GPT-4 today through the OpenAI API, you might think that you have some promise of stability and reproducibility, that like GPT-4 means it's one specific model and one specific build of that model, and that's going to be like the same thing. And if you just always use GPT-4, like if you use GPT-4 today, it'll be the same GPT-4 that you'll use a year from now. That's not how this works at all. New builds come out all the time, and not all model builders give you an easy way to access a specific build, not just the latest build. If you use the web interface, ChatGPT, you will see at the bottom of the browser, it will tell you this is, the version of GPT-4 that was built on X date. And that changes not with a regular schedule, just sort of whenever the model provider feels like it. There's not a release cadence. There's not a way to request a specific build yet. And this presents a real challenge to building and developing AI tools at production scale. And as I said before, we are in the infancy of large language models as a technology. They've been in the research phase for a long time, and only now are we starting to see that research bear fruit and us build real tools around large language models. And as we start to do that, things that made sense early in the evolution, early in the research process, may become limitations to scaling and to building actual production tools. So we've talked a bit about an analysis tool, and now it's time for the more unhinged part of this talk, where we try to get the AI to write code for us. So my buddy Connor and I have a podcast, ADSP, Algorithms Plus Data Structures Equals Programs. It's available on all streaming platforms. Go subscribe now. Link's right there. Anyways, said podcast led us to take a road trip across Slovenia a few weeks ago. And that road trip led to a discussion of how to implement std_unique in parallel. Std_unique is a C++ algorithm that takes a range as input and removes all consecutive duplicate elements from that range by shifting them in such a way that they will be overwritten. Consecutive duplicate elements are removed. That's important. It doesn't remove all duplicate elements, just consecutive duplicate ones. We had fun talking about this problem. So I figured that both GPT-4 and y'all might enjoy talking about it as well. So strap yourselves in. So here's an example of what unique does. Any place where we have a run of duplicate elements, it removes all but one. It doesn't sort the sequence. It doesn't assume that the sequence is sorted, and it doesn't remove non-consecutive duplicates. So the first two B's here, they are consecutive duplicate elements. So the second one is removed. The third B here is not consecutive with the other B's, so it's not removed. And the two C's here are not consecutive with any other C's, so neither of them are removed. So during our road trip, when we started talking about this problem, Connor, as he often does, quizzed me on how unique is implemented in Thrust. Thrust is NVIDIA's open source parallel algorithm library that inspired the standard C++ parallel algorithms. So most of these parallel algorithms are implemented as a composition of other algorithms with a few fundamental underlying algorithms like scans and reductions. I figured that this question was a good place to start with the AI. I was a little bit worried that the AI was going to do better on this quiz than me because I am terrible at these little quizzes that Connor likes to give me. But fortunately, I had nothing to fear because, of course, the AI told me that Thrust unique is implemented in terms of Thrust unique copy. I mean, it's not wrong, but it's also not right. Yes, that is technically correct. That is technically an answer to the question that we asked, but that wasn't really what we were asking. Okay, so I tried again. This time I asked it what unique copy is implemented in terms of. I didn't try to explain to it like that, hey, no, that's what I meant. I was like, all right, I'll just start off by asking what unique copy is implemented in terms of. Maybe that'll get us to a better answer. And what it told me is that it says that it can be implemented in terms of adjacent difference and copy if. It also says that it can be implemented from scratch using a combination of lower level operations like scanning and partitioning. We're not going to go into the details right now, but this is pretty close to being correct. Copy if and adjacent difference was the answer that I gave Connor. Connor actually asked me what two algorithms are thrust unique implemented in terms of, and I said copy if, and then eventually later I said adjacent difference. Okay, so now let's ask it to write some code for us. So we're going to ask it implement a parallel version of std_unique using only the standard C++ parallel algorithms. Here's what it gives us. That's once again, it has failed to understand the assignment. What it's given us is just, hey, okay, I'll just call the parallel overload of std_unique. But of course, like, this is not what we wanted. We want it to explain to us how we would implement the parallel version of std_unique, not just call it. Like, I can see how it came to this answer, but that's not really what we wanted. Now, in the AI's defense, there was maybe some implicit assumptions in the way that we asked our question here. That the AI didn't understand. And there's certainly a world in which this answer is reasonable. And it may be unreasonable for me to have been surprised at this response, because I only gave it this one sentence that was very simple. It didn't have any of the context of, oh, hey, I'm somebody who implements C++ standard libraries. Most programmers don't do that. Most programmers use C++ standard libraries. And so if most of the data out there in the wild is data about using C++ standard libraries, then when it encounters this prompt, it's not going to think like, oh, he means like, how do you write an implementation of the std_unique algorithm? It's going to maybe think that I meant like, oh, how do I use the parallel algorithms? And if the question that the user was asking is just, how do I use these C++ parallel algorithms? How do I use the parallel version of std_unique? And this is absolutely the right answer. However, it's the wrong answer for the question that I asked. And certainly when I asked it this way and it gave me this response, I sighed and I was like, that's not what I meant. So note that both in its explanation and its code, it states that there is a parallel version of the std_unique algorithm. But in other interactions, it claimed that there is no parallel overload of std_unique, even as of C++20. But that is wrong. That is incorrect. It is not true. That is information that it made up or hallucinated. And the AI often does that. It is prone to hallucinations. It is prone to making things up. You have to be a little bit of a skeptic anytime it tells you something that is factual. Okay, so later on, it gave me this gem for how you would implement a parallel unique. So it gave me this function parallel unique, takes 2 iterators. First of all, it sorts the input in parallel. We don't need to sort the input because unique only removes consecutive duplicate elements. I said that at the beginning, and I emphasized it a few times. This was a recurring issue in working with the AI on this particular problem. In many of its responses to my early prompts, it felt the need to sort the input. And then it calls std_unique, but it refuses to call the parallel overload in this particular case. And it explained to me that it didn't want to call the parallel overload of std_unique because it believes that it will be slower than just running it sequentially. It did call the parallel overload of std_sort, but for the call to unique, it did not. So it introduced some parallelism here, but the parallelism that it introduced was only to do an unnecessary operation that had nonlinear complexity. All right, great. So at this point, I was trying to figure out, how do you get a refund for your OpenAI subscription? I'm like, Googling OpenAI refund, like this thing is not, it's not doing what I want. Like, come on, do something smart, please. All right, so let's try this again. So I kept going, and eventually it gave me this response, which seemed a little bit better. So everybody take a second and look at this and see what you think about it. Maybe you can use the responses, give a thumbs up or thumbs down about whether you think this is good, whether you think this is bad. So there's a this is a correct answer. What it's doing here is it's creating an unordered set, and then it is going to insert each element into this set, and it's going to do that with a parallel remove if, which that's not really the right algorithm. It really should probably be like a for each for what it's doing here, but that's like a minor mistake. And it's using a mutex to protect access to the unordered set. So like this is a correct answer. However, this is like completely the wrong direction for what I had in mind. Because when I'm talking about a parallel algorithm, implementing a parallel algorithm like unique, I don't want to have to introduce a concurrent data structure like this. And one of the reasons is scalability. I work at NVIDIA. We make GPUs, which are massively parallel processors that have hundreds of thousands of threads. And something like this is not going to scale to hundreds of thousands of threads, because hundreds of thousands of threads trying to lock this mutex, that's going to be a huge contention point, and that's just going to be awfully slow. So when I'm writing parallel algorithms, I'm looking to write algorithms that don't need to do synchronization through a mutex or really through any synchronization primitive, but instead I'm looking to write algorithms that use underlying fundamental parallel algorithms like reductions and scans that can be implemented efficiently at scale, and that perform some form of communication as an inherent part of their algorithm. I'm not looking to do anything that does explicit communication through some synchronization primitive, and certainly not through a mutex. Okay, so here's another response that it gave me. So everybody take a look at this one, see what you think about this one. Again, give a thumbs up or thumbs down for how we feel about this. And as you're looking at it, I'll explain a little bit about what it's doing here. So the heart of what it's doing is it's doing a for each over a series of chunks. So it's breaking up the input into some chunks. The first part of the code here is just where it's figuring out the size of these chunks. It's calling them buckets. And then for each one of those buckets, it's going to go and do a local std unique on just that bucket. And then after, and it's doing each one of those local bucket uniques in parallel. And then after all of those, it is going to do some merge pass, where it combines information from all of the buckets to sort of fix up the result, so that the end result is actually unique. In the merge pass here, it may not be entirely correct. It probably has to still do some uniquing at the end here. But like the basic idea is go in parallel, unique each bucket, and then do some little work later to fix it up. So what do we think of this? Do we like this? Do we not like this? I'm seeing some thumbs up. All right, so this may be fine if you have like a few threads. But I work at NVIDIA. Again, I have hundreds of thousands of threads. And that second pass there, that merge pass is going to suck. It's going to become a bottleneck because we have to do that sequentially. And that pass is linear complexity in the number of threads that you have, or the number of buckets that you have. So if I have hundreds of thousands of threads, then that final merge pass is going to be very expensive. So in an analysis of this implementation of the algorithm, it's using OT temporary storage. So it's a one piece of temporary storage per thread. Which again, not great for scalability. It's got one parallel pass, and that parallel pass is just like a for each, which is good. And then it has one OT sequential pass. So this is like good, but not great. So my first 5 attempts to start on this problem with the AI failed, some miserably, some hilariously. And honestly, it was mostly my fault because there were a bunch of requirements that I had in my head, but that I had not expressed to the AI. There were a bunch of assumptions that I had that, that were not stated. And this is a common issue with automation tools like fuzzers and reducers. There's a tool called CReduce that you can use for reducing a C++ or C input test case that causes a compiler issue. And you can use this tool to reduce down the size of the input code that causes the compiler to reproduce this bug. And almost always the first time that somebody uses this CReduce tool, the tool reduces down the input to like an empty source file because you somehow didn't clearly state to the tool that like, hey, this is the particular compiler error diagnostic that I want. And so the tool just removed all the code and was like, oh, this reproduces, this passes the little test that you've given me. We often don't state our requirements correctly because we don't fully understand them ourselves, or there's a bunch of implicit context that maybe humans could figure out, but that an automated system wouldn't understand. And then we get surprised when an automated system produces output that fails to satisfy our unspoken requirements. That's very unreasonable of us. So I figured out what my requirements were, and then I stated them clearly, and I asked the AI to list some different approaches and to not show me any code yet. And that technique of asking it to list some different approaches and not show code proved to be very effective. And the requirements that I gave it was, I said clearly that std_unique only removes consecutive duplicate elements. So I gave it a clear definition of what I meant by std_unique, because in my previous prompts, I just said std_unique and expected it to figure it out. And I said, do not use the existing parallel overload of std_unique. I made it clear to it that I'm looking at implementing std_unique, not how I would use it. And then I also told it only use other standard C++ algorithms for parallelism. I don't want it to use OpenMP or TBB, and I don't want it to use std threads. It tried to use std threads in a bunch of examples too. And I told it, don't use any synchronization primitives like std mutex. Don't use std async and std future, nothing like that. Only use other standard C++ parallel algorithms. And I asked it to express their answer as a function that takes a single range. So these were all things that I had assumed in my initial prompt, but I had not clearly stated. And so that brought me to this prompt, this refined prompt, which is what finally got me to some successful answers from the AI. And the key thing to highlight in this prompt is the last line where I say, be concise in your reply and don't show me any code yet. I'm just asking it. And then at the beginning, I ask it to list multiple different approaches. So I gave it this, and then it came back to me with this. And here are the options that it gave me. So we can roll out 2 of these options pretty quickly. Option 4 is a parallel sort and unique. We told it we don't need to sort the input, but it ignored us. That's okay, though, because we asked it for multiple options. So it gave us one bad option, but we can just ignore that one and move on. Option 2 here. Let me see. Yeah, option 2 here doesn't satisfy our requirements. It does more work than we need to. So we can eliminate that one. Or option 4 also does more work than we need to, because it's a parallel sort and unique. It does that sort. We don't need that, so we can eliminate that. Option 3 is pretty similar in what's problematic. It's something that we've seen before. It's using a concurrent associative data structure. We saw an example of this earlier where it used an unordered set and a mutex. This approach will remove all duplicates, not just consecutive duplicates. So again, this is going to do more work than we need to do. So we can eliminate that option of option 3. Now, option 1 is splitting the input into chunks and having a thread unique each chunk and then doing a merge afterwards. We saw this basic idea earlier, and this actually has some merit. When Connor and I were talking about this problem on our road trip, he came up with that basic idea when we were brainstorming an optimal solution. I then pointed out to him that the issue is that it's not gonna be scalable because that merge pass is gonna be very expensive if you have a lot of threads. That merge pass will have number of threads, time complexity, which won't scale. Maybe we could find a way to parallelize the merge pass and ideally combine that into the first pass. Like that's an idea that might be worth exploring. However, what I'm interested in is exploring this second option here. That seems most appealing to me. In particular, I like the part here about calculating a binary flag for each element that indicates whether it's the same as the preceding element. Computing this sort of metadata with a scan is a very common pattern in parallel algorithms. Often, we don't need to actually store this metadata anywhere. It's just sort of conceptual. We build this metadata on the fly, but conceptually, we have a pass that builds a flag for each element that indicates whether it's the same as the preceding one, and then we do something based upon that. Now, there are parts of its answer here that sound wrong. It talks about doing a reduction at the end, which kind of sounds a little bit like nonsense because we're not looking for a single value, scalar value as a result. But it's okay that parts of this are wrong. Overall, this is close enough to being sensible, and we can work with the AI to refine it. So I tell it, okay, we're going to go with this approach. So I also mentioned to it that a scan may not be the right thing here. It suggested a scan, but I say that may not be right. And this is a little bit amusing because when Connor asked me about this problem, one of my first intuitions was that we could solve this with a scan. And he eventually talked me out of this. And in hindsight, that may have been a mistake. And maybe I shouldn't have told the AI to rethink the scan piece. And you're going to see why a little bit later. So it responded to my second prompt by describing the moral equivalent of an adjacent transform. I'd asked it, hey, what can we do instead of instead of a scan? How can we implement this? So it said we could do something that's the equivalent of an adjacent transform or an adjacent difference. So essentially an algorithm that will compare every two adjacent elements and outputs the result to a temporary array of flags. This seems to me like it's on the right track. Remember earlier, we said that thrust's unique copy is implemented in terms of adjacent difference and copy it. All right, so now we have a plan that seems reasonable. So now we allow it to write some code. I say, okay, go ahead and write me some code. And then it did something very interesting and clever. It said that it was going to use thrust. This was the first time that thrust was mentioned in this session. When we asked earlier about how thrust implements unique, that was in a separate session and not part of this context. This is a violation of our requirements. We said only use the standard C++ algorithms, but it's actually good intuition and it sort of was okay here. Because see, this whole problem is actually something of a trick question. One of the reasons I was so fascinated with this problem when I was talking about it with Connor was that I was unsure if the optimal solution can be expressed solely with standard C++ parallel algorithms. Okay, so here's the first code from this session. So it takes a vector as an input, which is not exactly what we asked for. And it creates not one, but two arrays of n temporary storage. It then does an adjacent transform that fills in this flags array with the result of comparing each two consecutive elements. Then it uses an inclusive scan with the flags array as input to determine which index each non-duplicate element needs to move to. This is a clever technique that Connor and I have seen a few times in parallel algorithms. It's beautiful, but we're not going to digress into the details of how this works today because we're going to get this refactored away. If you're interested, though, check out some of our other talks. And then it's going to use those computed indices to construct a thrust permutation iterator, which is a fancy iterator that provides a view that reorders your data. And then it's going to pass those iterators into thrust copy. So what do we think of this? It's okay. If we analyze this, all of those ON operations in this code are parallelized. and all of the sequential operations are O1. And that is great because it means that this will be scalable to hundreds of thousands of threads. However, we have 3 parallel passes, and we're using 2N temporary storage, the flags and the indices. Just ignore the output vector for now. That's going to be refactored later and is not inherent to the algorithm. So anytime that Connor and I talk about a parallel algorithm, my goal is to solve that algorithm in 1 parallel pass with no temporary storage and all sequential operations being O1. So I think that we can do better than this. So I asked the AI if we can combine some of these passes. I start off by asking it if about the inclusive scan and the copy passes. And it tells me that it thinks that this can be done with an inclusive scan by key. That didn't sound exactly right to me. I was thinking of can copy it. So I told it that, and it suggested that we should just use thrust unique by key. Now, this was again a moment where I was like, oh, come on, we've been doing so well. Like, the whole point here is to implement unique. We can't just implement unique by calling, unique by key. That defeats the whole purpose. Like, no, bad robot. So this was starting to go off the rails. So I decided to ask the AI to go back to brainstorming mode. And by that, I mean, I asked it for a list of options with no code. And it gave me these options. And some of these seemed okay. And it also, interestingly, it actually analyzed the list of options that it gave me. And it recommended the copy if option. That was my intuition as well. And so I told it to rewrite the code accordingly. And it produced this code here. Now, the version of copyif that it's using here isn't the one that we have in the standard library. It's a thrust extension. This overload takes an additional range called a stencil, which is passed to the predicate instead of the input sequence. And in this example here, that additional range is this range of flags that's constructed by the thrust transform directly above this copyif. So essentially, this copyif allows you to separate the decision about what to copy from the thing that you are copying. So with this, copyif will copy from data, and it will only copy the elements of data for which the corresponding elements of flags are true, and it will copy to output. Now, creating this output vector that we later swap with data seems wrong. Unique is supposed to be done in place, and copyif can be done in place. So we should just operate in place and avoid this allocation. It's also a bit odd to have this function take a device vector instead of a pair of iterators. And that's not what we originally asked it for. So next I asked it to refactor the code to take a pair of iterators instead of a device vector. And here's what it gave me. So no more device vector in the interface and no more output vector. So take a moment, look at this. This is a little bit simpler, a little bit easier for us to understand. So it does essentially 2 things. It creates this flags vector, and then it computes the flags where each flag says whether each 2 adjacent elements are equal. And then it uses those flags to copy only the non-duplicate elements into the output. And that essentially will shift everything doing the unique operation. So this is pretty good. This is better. We're down to 2 parallel passes and only in temporary storage. That's an improvement over before where we had 2N temporary storage and 3 parallel passes. But I think we can do better. So I ask it to go back into brainstorming mode, and I tell it that I want ON temporary storage. And here's what it got for me. It gives me these options here, and looking over them, a couple of them sort of suggests the same path more or less. But the one that's most interesting to me is this one, option 2, where it suggests using zip iterators to further refactor the code. And that sounded like the right sort of approach to me. So I tell it, okay, let's go ahead and do that. And so here's what it gave me. So it's using the zip iterators here. So it's zipping up two sequences. The first sequence is from the first element to the second to last element. And the second sequence is from the second element to the last element. And this gives us adjacent pairs of elements. So this looks much better to me. We have one parallel pass and no ON temporary storage. That's great. However, it's added this nasty special case for the last element. This looked ugly, potentially buggy, and a bit unnecessary to me. So I asked it if it could remove this. And it gave me 9 different options, none of which seemed correct. So I told it to forget about this idea of removing that piece of the code and that we'd move on to something else. And a little bit of foreshadowing here, trying to move on after I told it to solve this problem proved to be a mistake. So next, I pointed out a bug to it. When we combined the first pass into the second pass, we switched from the stenciled version of copyIf to the traditional one that takes an input range and an output range. The input to that copyIf is a range of tuples of adjacent elements. The output is an iterator to the original range. This copyIf will try to assign the tuples of adjacent elements to the elements of the original range, which is wrong. It's going to try to assign a tuple of TT to a T. That's not going to work. So I asked the AI to fix this. First, it wanted to use remove copyIf, which didn't make a lot of sense as it would have the same problem. And then in its explanation of the refactor, it mentioned that the refactor would remove the need for handling the last element specially. Now, that was correct, but that isn't really the problem that we were trying to solve right now. We were just trying to call the correct version of copyIf. But it was confused because we'd asked it earlier, hey, remove that special handling of the last element. And then we told it to forget about that and move on, but it didn't really forget about that because that part of the interaction was still in the context window. And so it got confused. And I've found that large language models work best when you go step by step. And if you try to get them to do too many things at once, you're much more likely to get some nonsense. So eventually I convinced it to fix the problem and to go back to using the stenciled copyIf overload. And then it had this code, which is a lot simpler, looking pretty good. So again, this says copy elements from the range first last to the range first, passing corresponding elements from the range zip again to the predicate to decide which elements should be copied. And the range zip again is just a range of the every 2 adjacent elements. So next, I asked it to replace the thrust zip iterators with standard C++ range views. And here was its first attempt using C++ 23's zip view. Now, there's a couple problems with how it's constructing the zip view here. It figured out how to use thrust zip iterators correctly in the first try, but it got pretty confused here. We don't really need to use take here. What we want is a range of adjacent elements. We create that by zipping a range from the first element to the second from last element, and a range from the second element to the last element. It's trying to use take to produce that first range, but that's unnecessary. Zip will be sized to the smallest range you pass to it and will truncate the other ranges. So we can just pass the entire range as the first argument. Another problem is that take and drop take a range as an argument and not an iterator. So I had it fix these problems in a few steps. First, I had it change parallel unique to take a range, not a pair of iterators. And then I told it that using take seemed wrong, and I asked it to explain why we needed to use take and if it was sure that that was correct. It realized that it didn't need to do that, and it just got rid of take entirely. Then we realized that we don't even need to use zip. There's an adjacent view that does the same thing. So it just decided to use that instead. I said, hey, yeah, you can just use that instead. And at this point, I was starting to run out of ideas, and the code was looking pretty good. So then I decided I was going to ask the AI if there were any bugs in the code. That sounds a little bit weird, right? Have you ever asked your coworker in a code review, like, hey, are there any bugs in the code that you wrote? Well, like, obviously, if they knew of some bugs, they wouldn't have, showed you the code. But actually, maybe this is a question that we should ask more, because sometimes there are bugs that you know about. And it's actually a great technique for the AI. Ask it to analyze its own code. Earlier, when it gave us a list of options at one point, it did its own analysis and it said, hey, I gave you these 4 options, but I really think that this option with CopyIf is the best one. And it turned out to be right. You can ask the AI to analyze ideas that it brainstormed with you. That's a really good approach. So it did find a problem here. You see the predicate here? The predicate as written will keep all consecutive duplicates and remove any unique elements. And that is the inverse of what we wanted. And it points that out. And I asked it to fix that. And it gave me back this code here, which fixes that problem. But interestingly, it re-added the manual handling of the last element. Remember that before we had tried to remove this, gave up, and then attempted to move on, but it didn't really listen to me, and it kept trying to get rid of that special case for the last element. And in a subsequent unrelated refactoring, when I had asked it to switch back to the stenciled overload of CopyIf, it removed the manual handling, and I didn't realize that when it did, it had inverted the predicate and completely broken the code. And I believe that it did that it made that mistake because I had given it I'd made that prior attempt to tell it, hey, get rid of that manual handling. And I hadn't seen that through to completion, and that had confused it. So I think that bug stemmed from my initial ill-thought attempt to tell it to move on while we were doing a thing. I should have instead worked with it and completed that particular task of removing that special casing for the last element, and then moved on to another thing instead of just trying to be like, hey, forget about it, let's go on and do something else. So the correct way to get rid of the special case for the last element is to change the output range to start at the second element and always keep the first element. We're doing all of this in place, so we don't even have to do anything to retain the first element because the output is the input. So then for each pair of adjacent elements, you can pair them. And if they're not equal, you keep the right element. And if they aren't equal, then you omit the right element. And you do this for the entire sequence. And this is the optimal parallel implementation. So I tried brainstorming with it to see if it could figure this out on its own, but it didn't. So I just nudged it a little bit in the right direction and told it that instead of manually handling the last element, how about just having the output range for the transform if start at the second element instead of the first? And then it figured out, aha, that is, I see what you want me to do there. I got it. And then it gave me this code here. So see, the output now starts at the second element, which is what we wanted. However, it has now added this nonsensical manual handling for the first element. And I asked it about this. I was like, hey, like what you're doing here is you're assigning to the first element and you're assigning from the first element, like this assignment is already true. Do we really need to do this? And it thought about it and I was like, no, okay, yeah, like I understand what you're saying here. I made a mistake, and it got rid of that. And then it came up with this as the final form of the code. And this is great. This has no temporary storage and just one parallel pass, which is just this one CopyIf that uses this stenciled overload that takes an adjacent view of the input sequence and uses that to decide which elements to copy. So you may be wondering whether this exercise was truly valuable. It seems like a lot of this was me leading the AI to the right answer. And I think that may be true, but that doesn't necessarily mean it's not valuable. It's sort of like working with a junior engineer. It certainly saved me a lot of time in searching for the optimal solution here. And I actually think that I made as many mistakes as the AI did, and I often guided it in the wrong direction. And that was sort of an interesting and eye-opening experience for me. Earlier, when we had 3 parallel passes, like a good while back, I asked the AI to combine the inclusive scan and copy passes into a single pass. And it suggested using inclusive scan by key, which I dismissed, even though my initial intuition when I discussed this with Connor was that this could be solved with the scan. But after my discussion with Connor, I became convinced I was wrong. And so I dismissed that idea when the AI brought it up. And our final solution turned out to just be a CopyIf. But a parallel CopyIf is actually just implemented using a form of scan. It's known as something called stream compactation in the GPU world. Most parallel algorithms boil down to either a for each, a reduce, or a scan. I'm not exactly sure where the AI would have taken us if we had followed that path of doing inclusive scan by key. But given that a copy-if is actually implemented in terms of a scan, I'm pretty sure that that would have led to an equivalent correct answer. But I dismissed that possibility, and I maybe ended up creating more work for myself because of it. I also missed multiple bugs that were introduced due to my misunderstandings or refactoring mistakes, such as when I asked it to remove the special case for the last element. I failed to understand that it wasn't starting output at the second element, and thus that special case was necessary. Anyways, I'm pretty happy with the code that we have, but we're still using Thrust and not the C++ standard library. So I asked it if we could use the C++ standard library's parallel copy-if instead of Thrusts. And it pointed out that the C++ standard library does not have a stenciled copy-if overload. Remember, back when I started in this problem, I said one of the reasons why I was interested in this particular problem was that I was not sure whether you could write the optimal implementation of this parallel algorithm using only the standard C++ parallel algorithms. And it turns out that you can't, because we don't have that stenciled copy-if overload. The primitive that we need, we don't actually have in the C++ standard library. So then I asked it how we could make it possible to write this in standard C++. And it suggested that we write a C++ committee proposal adding some missing algorithms, such as a stenciled copy-if. So then I asked it for an outline for this proposal, and then we iterated on that a little bit. And then I asked it to start writing the proposal, but that will be a different talk. So I'm going to wrap up now and give you a couple of my conclusions from this experiment. So giving AI roles is an incredibly powerful tool. That can be telling it to act as if it was a certain type of person, or something as simple as what we did. We told it at times to brainstorm and list ideas without code, and then at other times to write code for us and then refine it in a certain way. And switching between these two modes was very powerful. When you are constructing an algorithm like this, you're essentially doing two different creative tasks. One, you are designing and brainstorming, you're thinking up strategies. And then two, you are writing actual code and solving issues in that code, removing bugs from that code, refactoring that code, etc. Those are two distinct roles, and separating those roles was very helpful in getting to a correct answer. When the AI responds to you, it has many different ideas, possible paths that it can take, and a lot of those paths can lead to nonsense. A naive prompt might lead the AI to just give you its best answer, which may not be great. By asking it for options, by asking it to list options, to brainstorm with us, to give us multiple different approaches to consider, and then guiding it towards the one that we want, we get to see more of the tree of possible responses that the AI has. And that gives us more visibility into its thought process and gives us more options. And ultimately that can lead to better outcomes. So one of my takeaways is work step by step, guide the AI. And if you don't know what the steps are, figuring that out is in fact the first step. One of the major limitations of large language models is their sensitivity to the text of the prompt. There's often not a clear fixed point prompt that robustly generates good code. I iterated 5 or 6 times on an initial prompt before the one that led to that successful session where we wrote the code. And the first 5 times, the response was, so off that I just was like, I'm going to completely close the session and try again. You often have to spend a lot of effort prompt engineering to produce good results. And a lot of this prompt engineering is model and model version specific. And one of the challenges here is that once you've started a session and once you're like deep in a session, if you make a mistake, if you tell it something that leads it astray, like when I asked it to remove that special handling of the last element, it's really hard to sort of roll back and go back to an earlier point in the conversation. There's no way to just like git fork an existing AI session, which makes it really hard to refine and improve your prompting strategy and get to correct answers, because sometimes you can't just tell it, hey, forget about that and move on. And I think that we're going to see down the road ways to copy just part of a session or to create forks of a session. And I think that that'll be a very powerful tool that'll make it a lot easier to work with these models. Most of the popular large language models, yeah, I'm like a couple minutes away.
Yeah,
I'll be done in like two to 3 minutes. Most of the popular large language models take critique in a non-human manner. They always agree, but they often don't understand or act on exegesis. Answers can become increasingly off track with time, and forced niceness can make it unreliable. It should be easier for these models to be able to say no or I can't. I think that we often judge AI unfairly because we expect a neural network model to produce the sort of complex thoughts that humans do. Do you write code that runs correctly on the first try? Is your first thought always your best thought? Why would we expect anything better from AI? We think iteratively, we refine our thoughts, we have internal monologue. Neural networks alone do none of that. But we can build more complex AI systems that do. So analysis, in conclusion, analysis tasks, I think, are an excellent fit for AI, and creation is harder. Success with AI models for software engineering requires skill. We should all be developing that skill. And you should all be thinking about how to integrate AI into your existing workflows today and explore how AI will change how we will work in the future. I think AI will be like version control for the software industry. It will become normalized and ubiquitous, and it will improve the quality of the work that we do. It won't happen overnight, but it will happen. So start learning to use it today. That's all. I'm sorry. I know I ran a little bit over time there, and I went a little bit fast at the end. But I hope that was valuable to everybody. I will be in the Discord to answer questions. So thank you so much. And I hope to see you at next year's conference.